Okay, let's do a few sample equilibrium problems that use the concept of mechanical equilibrium to find unknown quantities. So here we have a situation where we have a 2 meter long steel beam that's 40 kilograms that is suspended horizontally from a pivot, like a hinge on the side of a building, and an angled cable. This would be something like, for example, you might hang a sign from or things. So what we want to know is what's the tension in the cable? So like, how strong of a cable do we need? And what is the forces acting at this pin, this hinge pin, so we can know how big of a diameter bolt we need to put in that hinge. So this would be a typical thing where you use equilibrium to find quantities like um, the physical forces involved in the problem. So we're going to apply our concept of mechanical equilibrium, which has two conditions. And those two conditions are as follows. The sum of the force vectors on an object has to equal zero, and the sum of the torque vectors on an object has to equal zero. So this is our condition for mechanical equilibrium. So we just now need to figure out a way to use that information in a problem-solving strategy. So typically what we do is we look at the object and draw a free body diagram like the old days, when we want to try and solve for the sum of the forces problem. So I'm going to go ahead and represent this bar as a dot, as free bodies typically are represented that way. And we're going to apply a tension vector on the bar, T, at an angle of 35 degrees. We know that the bar has some weight, so there's going to be a weight vector, mg, pointed downward. And then there's some forces acting because there's a hinge pin over here. That hinge could very well be pushing out from the building, which we'll call this F sub x. And then it could also be pushing either up or down on the bar. So I will assume that it's helping to hold the bar up, F sub x, F sub y. Those are my four forces that I can see acting on this object. So this is a traditional Newton's law problem, Newton's second law problem. So I can apply sum of the forces is equal to zero, which means that the sum of the forces in the x direction have to equal zero, and the sum of the forces in the y direction have to equal zero. So I can expand those equations out from my diagram. I see that Fx points in the x direction, and I see that the x component of the tension points also in the x direction. So if I were to break this into components, I would get a t sub x going this direction and a t sub y pointed this direction. So I'm going to go ahead and put those into my x direction equation. So it's going to the left, so it's going to be negative t cosine 35 degrees. And in the y direction, I have f sub y plus t sine 35 degrees minus mg. 3 y forces, 2 x forces. And since we're in equilibrium, both of those are equal to 0. You'll notice I have several unknowns. I have an fx, an fy, and a t. Those three unknowns, I better have three equations. And where am I going to get that third equation from? Well, I'm going to get it from here. I'm going to get it from the torques. So now I have to learn how to do a torque problem um, from this diagram. It's a little harder to do a torque problem from a free body, so we have to go back to our original picture, because remember that torque is R cross F, or RF sine theta. We need to know how far away from a pivot point, and we need to know the angle between the force and the radius. So we need to come back to our original diagram. So I'm going to try and draw over top of this one in maybe a different color, like green. So first thing we have to do, step one, is we pick a pivot point. Sometimes a problem will lead to a natural pivot location. In this case, the natural pivot location for us to talk about is this hinge point on the left-hand side. So I'm going to count that as my pivot point, and now I'm going to measure radii and, and angles with respect to that pivot point. So the the first force in my diagram, remember I have a force uh, F sub y and an F sub x from the pivot. Both of those forces, any forces that pass through the pivot uh, don't contribute torque because R is 0 in those cases, so R cross F is 0. So I can ignore those. So let's go ahead on to my next force. My next force is my weight. And you'll notice that I'm drawing this weight vector, mg, at the center of the beam. This introduces the concept of the center of gravity of an object. In a uniform object, the weight vector is considered to pass through the center of the object. If the object is non-uniform or funny shaped, then the center of gravity is the center of mass of the object, and we can talk about that at another time. But in these uniform cases, it's through the center. So if you'll notice, then my pivot point is 1 meter away from where my force is acting. That distance is 1 meter. So the first torque, so if I'm doing sum of the torques, I'm going to do 1 meter times mg, which would be 40 kilograms times 9.8 meters per second squared. And now I have to decide, is this going to be a positive or negative torque? Well, this is tending to rotate the object clockwise, and we talked about clockwise being negative. So my first torque is that. Now I think of my next force is my tension being applied way out here at the end. So I have a radius vector that goes all the way from here out to here, and I think this is 1.95 meters according to my diagram. So that tension is going to tend to turn this thing counterclockwise, so that gives positive torque. And so we're going to have 1.95 meters times t times the sine of the angle in between them. And I apologize, I skipped my sine of my angle in here. Sine of the angle between R and F on my first term. Well, R was pointing along the length of the bar, and F was pointing straight downwards, so that made a 90-degree angle. So this was sine of 90 degrees, and that's why I dropped it out. I was lazy and didn't write it. Sine of 90 is 1, and so it will disappear. And here I need the sine of the angle in between them. So let me go ahead and rewrite this in a little bit cleaner. So this is going to equal negative 40 times 9.8. So negative 392 meter newtons worth of torque plus 1.95 t times the sine of something. And now we need to figure out what that angle is. Well, R points along the length of my rod, and so T points this way, so I have that angle all the way around there. Well, that's going to be an angle of 180 degrees minus 35, or 145 degrees. So we now have an equation that says this. You'll notice that in this equation, fx and fy do not apply because we picked our pivot point that eliminated them. So as a result, we can solve this equation for t. The tension is going to equal 392 meter newtons worth of torque divided by 1.19, and I should have been careful with my units there. That is meters from above, and this should give me then an answer that is in newtons for a force. So our torque, our tension in our string is 329 newtons. That helps us because now that eliminates from each of these equations one of the unknowns. So I can take this top sum of the forces in the x direction equation and write it as fx minus 329 cosine 35 degrees equals 0, or fx is equal to 329 cosine 35 degrees, or 270 newtons. And then Fy is going to equal, sorry, I'll go ahead and write it out. Fy plus 329 sine 35 degrees minus mg, which was 40 kilograms times 9.8 equals 0. So I can solve that for f sub y. And f sub y turns out to be 203 newtons, and the significance here is f sub y turns out to be positive. So the hinge is in fact helping to hold the object upward. If we had ended up with this 203 newtons as a negative quantity, that would have told us that the hinge was pulling the object down. The solutions will always work, um, even if you just pick a direction and stick with it. The positive and negative nature of vectors will come through in the end to tell you whether you're right or wrong. So here's a classic example of an equilibrium problem where you use sum of the forces equal to 0 and sum of the torques equal to 0.